So, yeah, I'm going to talk about these transfer systems again, and kind of the idea is that at least more than one of you in this room has emailed me at some point asking how many transfer systems are this. Send you back like a one-line reply with a number, and you just take my word for it, this number's correct, which is very kind of people. So I want to start by talking about how do we actually compute the number of transfer systems for things, what methods do we have, what methods am I currently using, and then, by seriously considering the algorithms we can use to generate these things, well, let's consider some kind of new invariants of groups, which I think are very interesting. So some of what I'll be talking about is joint work with Catherine Derek, Miguel Barrera here, Stephen Schreier, Noah Wisdom, and Valentina Castro. So we've seen this definition a few times already. So G transfer system, I pick a finite group G. I look at these intervals, so pairs of subgroups HK, and I ask that I have all these identity. So I'm going to do mine as pairs throughout this talk. I have all the identity pairs. I can compose the pairs. We have this restriction rule that's been mentioned a few times. And I very seriously do want to consider conjugation today. A lot of the talks have considered abelian groups, but what I'm going to say kind of works in the full generality. And seeing as I'm getting a slide talk, I decided to use pictures today. I wanted, for reasons that will become apparent later, one of the kind of classic covers of Moby Dick. I really enjoy kind of these book covers from the 60s, they're wild. Anyway, so I came across the fact that before Marvel were remaking Fantastic Four for the fourth time, they had this run 50 years ago of classic books in comic form. And I'm going to use these kind of guide the conversation a little bit. You can, so why not? So how do I compute the transfer system for G? And what we have is like this bag of parts which we can apply, hence Frankenstein. So the first idea, brute force. I mean, that's always a great idea, right? So you take your subgroup lattice sub G, and you can just check all different subgraphs and say, hey, is this a transfer system? You can do this. This is how I used to do this back when the first paper came out on these things. But if I let iota be the number of non-trivial pairs, hk, so H is a proper subgroup of K, then you're reduced to checking 2 to the iota things, and that's a lot, right? So if I take this square free cyclic group, there's 3 to the n minus 2 to the n non-trivial edges, and like n is 5, then like 10 to the 63 is a lot. That's more than a lot. That's never going to happen. So this is okay for small things, but we have to be clever, which is, sometimes a nice thing. There's a few other methods kind of lying around the literature these days. I just want to give a very brief overview of what's out there. I don't know if maybe Angelica might talk more about some of these things tomorrow, but you could do like a recursion style thing. So you take your subgroup lattice sub G and you break it into these smaller pieces. And you say, if I can compute things on the smaller pieces, is this going to allow me to assemble all the data for transfers on G? And sometimes, yeah. So in this paper of myself, Dave, and Constanza, where we proved that the number of CP to the N transfer systems is bijection Catalan numbers, our proof goes by a recursive method. Have this over operation. And then myself, Kyle Ormsby, and Ethan McGraw kind of went further with this, and we've got a recursive count for transfer systems on C, P to the N cubed. So this is one method we have. Lattice constructions, and this is basically a non-starter from the get-go. So you ask, I take a lattice construction, like the product of lattices, does this mesh well with transfer systems? No, absolutely not. I mean, there's 2 transfer systems on this poster here, and there's 10 on here. And if maybe you've seen Constanza talk about these things, you would have heard the word chicken foot at some point. This is a transfer system which I just cannot see only using transfers on one. So this doesn't work well, but there is this one paper. I'm not even going to attempt to remember all these authors. I'm very sorry if any of you are here. They have this fusion product, let's say a fusion product of lattices. This gives me something on the transfer side, and they use this to enumerate transfer systems for rank 2 elementary abelian groups. And then the final thing, like my bag of tricks, is this losslessness. I'm sure we all felt that at some point. So transfer systems close up to conjugacy, right? So you say, just work on the subgroup lattice conjugacy. Well, this is now post-set, not lattice, but technicalities aside, why not just do this? And Problem is you can't in most cases, but sometimes you can. So again, with Carl and Ethan, we have this notion of a lossless group, and it says, hey, you can work on sub G mod G plus some conditions, and this works just fine. And we use this to do EP to the end for P and R prime. And as far as I'm aware, like these are all the theoretical tricks we have in our bag. And last year, I found myself with too much time on my hands, as one does. And I was like, what about S4? Like, I like the group S4. It's a small group. How bad could it actually be? And this became my obsession. So the number of non-trivial inclusions in this transfer last is 120. 10 to the 36, like my laptop's not going to be happy with me asking it to check these many things. S4 is kind of the easiest group we have that's not lossless. This was already observed by Ruben back in the day. I have the 3 Klein 4s, including into these 3 dihedral groups. And I have to actually remember which Klein 4 is in which dihedral group. I can't just say smear it up to conjugacy. So it's not lossless, there's no recursive approach, and this annoyed me for a very long time. And I'm going to tell you how you can get over this and actually compute the number of transfer systems for S4, and then this kind of crazy rabbit hole this leads to. So the key input is something that happens in an appendix of one of Ruben's papers. He says the following. So I'm going to take my subgroup lattice sub G. This bold I is going to be the intervals in the subgroup lattice. So just pairs HK, where H is the subgroup K. He says, take any collection, and I can cook up for you a transfer system. So you start by just closing under all conjugates. That's what this does. And then you close under the restriction rule, and then you close under composition. And you have to do it in this order. If you're in another order, you don't get a transfer system. But he proves for us that this S3 at the bottom here is the minimal G transfer system containing S. That's a nice idea. And actually, here's an example. So S3. So I take this singular non-trivial inclusion from the subgroup generated by the transmission 1, 2 into S3. So Ruben says close under conjugation. So I close under conjugation. Then I have to close under this restriction rule. And now you have to really remember, although all of the C2 subgroups are conjugate, I mean, they're not the same, right? If I intersect the subgroup generated by 1, 2 with the one generated by 1, 3, this is the identities. This actually fills out a lot. You get all of these 4 bottom inclusions just by filling out the restrictions. And then I have one composition from the bottom to the top here, and I've gone too far. But this is kind of crazy, right? All I did was specify a single non-trivial inclusion, and it's filled out basically everything for me. And it's like, why do I carry around all the baggage when all I need to remember is that single edge, which determines the rest? So this is the key idea, and we can recast this. So closure operators, we've all seen closure operators. I know we've had a lot of infinity categories this week, but like at some point you did point set topology and you actually cared about, spaces and closures of points. And this is just a generalization of this. So I take any set X and I look at its power set. So a closure operator is just something that goes from the power set to the power set. So A is contained in its closure. We believe that. A is contained in B. And the closure of A is contained in the closure of B, and it's idempotent. So if I take the closure of the closure, then this is just a closure. And again, from point set topology, a subset is just closed if it equals its closure. So why is this relevant? Well, Ruben's algorithm is a closure operator. So it goes from the power set of intervals on sub G to the power set of intervals on sub G. And the closed sets are the transfer systems. And all I've done is told you there's an algorithm, I've put it in different words, and now I expect you to clap, right? No, the missing link is the following. So, yeah, a crazy time machine, right, in the numbers. So there's really good algorithms for finding closed sets of a closure operator in the literature. Back in the 1980s, people were doing formal concept analysis. So think databases, like actual computer scientists really needed good algorithms for doing this. Database searching and stuff like this can be recast as closure operators. So they sat down, they wrote some very impressive algorithms that find closure operators. These have great time and space complexity. And we can implement it and do the same for transfer systems. And I've got this is a technical term, embarrassingly parallel. I didn't make that up. That is the technical term, check Wikipedia. went to Wikipedia, everything wrong. What this means is I can do a load of checks. I can just send them off to different places. Like I can send it off to a different computer, let it do its own thing. It sends some numbers back. I never needed to know what it did. So this is great. You can write algorithms for this, and I have written algorithms for this that do this in parallel. It sends it off to all your laptop cores, your laptop cries for 10 minutes, returns a number at the end. But these algorithms are extremely fast. They're very good. So I want to kind of just describe how this algorithm works. Again, just because so many people have asked me for these numbers, and on good faith, you just take my word for it, and it feels a bit strange at times. So we've seen this subgroup lattice a few times already this week. So this is CP squared Q or C12. Doesn't really matter. It's showing up very faint, but I have drawn in just all the inclusions. So we start with the empty thing. This is the closure of the empty set, right? Then what the algorithm says is I take each non-trivial edge, I add it in, and I take its closure under Rubin's algorithm. So this is what the next slide does. So for example, here, I've added in this edge here, I've done Rubin's algorithm, and this closes up here. And this gives me a bunch of new transfer systems. And what I have is I have this big bag in my computer, and I just shove them in. And this rejects things if it's seen it before. And if it's not seen it before, it takes it in. And what I do is I keep track of the new things that I've just seen. So these are all new things. So that was the first step. Then what we do is we take each one of these things, and then I add in an edge that's missing. I close it up into Rubin's algorithm, and I see if the bag wants it or not. If the bag takes it, I'm like, great, this is a new thing. And if not, it just kind of falls away and we don't think about it again. So the second step of the algorithm, I don't expect anyone to actually appreciate this slide. It looks like this. You get quite a few things. These are all brand new. And then you could do the same. You're like, I still have new things. So I'm going to add in an edge that they haven't seen, close up under Rubin's algorithm, see what's new again. And you get this. And at the bottom here, you see we found the complete transfer system. Algorithm's done. No. This pops out at the next step. There's only one. This appears in the fourth step of the algorithm. The complete thing appears in the third step, and you're like, yeah, your code's wrong. No, like this is actually a feature of transfer systems. This is not a bug, and I will discuss this feature later on in the talk. But this crops up at the end, and this is yeah, these things are strange. So that's how the algorithm works. This works exceedingly well for things we'll see in a second. So what this allows me to do is I can kind of partition the collection of transfer systems by what generation step they appear in. This gives a nice filtration. I haven't really thought about this beyond this slide, but I reckon if one was to take a group they're interested in, it's easier to compute transfer systems generated by last step than to say, let's do everything at once, right? We like splitting problems up into smaller problems. And there's actually a paper of Francher, Ormsby, Orsono, Quinn, and Blah. Yep. Yes. Where they actually do this with CP to the end. They prove that these numbers that pop up here are the Maruyama numbers. So this has been considered before, but only for CP to the end. And I'm saying, let's just do it in general. These numbers seem quite interesting. This gives us some fun things. I spent, like I said, far too long last year coding this. So I already knew the number of this PQRS. So James Crouch provided this number to me 5 years ago. My code was nowhere close to getting this number, and it always frustrated me. But now I can get it, so I'm happy. And I got S4 finally. So we saw that, you know, at most there were going to be 2 to the 120 transfer systems. It turns out there's only 8,691. So basically, you're never a transfer system. This is because conjugation is like overpowered, right? We've already seen in S3, as soon as I have one edge and I conjugate it, it fills out so much. So because things are so conjugative, I mean, this goes down very quickly. This only takes about a second to run, which is very nice. And I will say simple groups in general seem to be very good with this algorithm because everything just immediately collapses. And then, because I could, I did S5. What did I gain from this? Nothing. A sense of accomplishment, maybe. I wanted to know how far this algorithm I could push this. Very lucky at Queens, we have an HPC cluster. Sent it off, optimized the code, left it, took 6 days to run. I think at one point it was using 150 gigabytes of RAM. But this number came out at the end. I was very happy with this. We had 6 days to get this. So I've written some algorithms. I've got some numbers, but what is kind of any theoretical meaning of this, right? It should link back somehow to some problems, and this actually gives us a notion of something called a minimal basis for a transfer system. So I take some transfer system G and I look at a subset of kind of edges in there, S, and I say it's a minimal generating set if, when I apply Rubin's algorithm, I get the transfer system, and I have no redundant edges, so I can't remove anything and still generate the transfer system. Okay, what's nice is, although they're not unique, we'll see this in a minute, all minimal generating sets for T have the same size. You can prove this. And I'm going to ignore trivial edges kind of H to H from now on, because like my computer doesn't care about those, right? I mean, it has to have them, so they're there. And this number, this M of T, is how I'm going to define it. So this is the size of the minimal generating set, is exactly the step in the algorithm where the transfer system is generated. This tells me exactly how many edges I need to generate the transfer system. So here's an example. So here's the complete transfer system we saw, and all I need is this edge, and this edge. If you close this up under restriction and then composition, you get everything. So I only need these 3 norms before I get the full transfer system. And here's that kind of weird one that pops out at the end, and indeed, this has a minimal basis size of 4. I can't generate this with any less than 4 edges. None of these are redundant, and there's no better way of doing it. I mean, if you're bored right now, you just draw that down and just tell me it can't be done better, and I can sleep easier at night. So I have this number, this M of T, which seems to be some assignment from a transfer system to a number, and this is what I want to investigate. So like I said, minimal bases need not be unique, that's fine, but they all have the same size, so this is well defined. I take a particular minimal basis by just running Rubin's algorithm in reverse. So I start by removing edges which are composites, so I don't favor long edges, I favor short edges. I remove edges which I get via restrictions, and then I choose conjugacy classes. Never a good thing to choose conjugacy classes, but here we are. I just pick one, and it's fine. So before I move on to kind of combinatorics about these things, I just want to float a potential theoretical application of this. So I take a G spectrum X. Can I check X as an n-infinity algebra by just checking basis elements in these transfer systems, right? So I take something that's C12 equivariant, I want to check it's genuinely equivariant. I don't have to check the existence of all those norm maps. What if I could just check the existence of 3 norm maps and it gives me everything else? So this is where, I mean, I was like, how hard could this be? Very hard. But I think at this point, signs point to maybe this might be true. So this work of Hiller from a while back, which I think has some pieces we need. Lucy Yang has some work which does it for CP, which makes me hopeful. The other day on the archive, there's this new paper of Lenz, Linksens, and Kuchtuk, which seems to basically verify this for the complete transfer system. So for genuine equivariant things, this doesn't seem completely crazy anymore. And we saw on Monday, Natalie gave a talk and discussed the fact that if you take joins of the operads, right, then this seems to act nicely as well. So there seems to be certain theoretical signs pointing to yes, and I think this would be really nice if you just have to check basis elements for things. But I don't want to talk about this today, mainly because I don't really understand completely what's going on, and one shouldn't give talks about things that they don't know what they're on about. So what do I actually want to talk about? What can this maximally sized kind of minimal basis look like? Does it play with other concepts? I'm not going to talk about this today, but what do I mean by this? So we've had a few talks already this week, model structures from transfer systems, compatible pairs from transfer systems. I expect we're going to see a few more things in the week. But can I just check things on basis elements? Like, can I just say, here are two transfer systems, here are their basis elements. Is it a compatible pair? Do I have to really do all the hard work, or can the basis elements do the heavy lifting for us? I've already mentioned about filtering transfer systems on G by the size of the minimal basis. And I think what I'm going to talk about today, or what I am going to talk about today, because I know it's on the slides, are the fact that these seem to give new group invariants, which are actually genuinely interesting. So my first group invariant that I'm going to introduce is this concept of width. So C is going to be my notation for the complete transfer system for a finite group G. And I say, how many elements are in the minimal basis for the complete transfer system? So we've seen for C12 that this number was 3. And here are some other numbers. So when you first look at these, it seems random. So we have Cp to the n, this is n. So for Cp to the n, the subgroup lattice is just the linear order of a line, and you have to have each little segment of that line to complete everything. You can't get away with anything less. For grids, so for Cp to the n, q to the m, I have n plus m things going on. And we'll see why in a minute, but maybe I will use the board for a second. So if I have my grid like this, so here's E and here's Cp squared, Q squared. And what I need is I need this edge, I need this edge, this edge, and this edge. And this will give you everything. And basically it's a game of staring at these things long enough. So for square-free cyclic groups, so Cp1 up to Cpn for distinct primes, the number's n, this is nice. For abelian, elementary abelian p groups, this is p to the n minus 1. At this point, some of you have already clocked onto what's happening. For S4, the number's 5. For S5, the number's 7. These seem pretty much pulled out of thin air and maybe mysterious. But there's rhyme and reason here. So let me introduce a particular type of subgroup of the group. So let G be a finite group. It doesn't have to be finite, but let's make it finite. So a proper subgroup H of G is meet irreducible if I cannot write its intersection of two proper subgroups. I'm going to know these by Mi of G, these meet irreducible subgroups, and you immediately see all maximal subgroups have to be meet irreducible. That's pretty clear, but there are other ones as well. So here, this subgroup Cp squared is not maximal, but it is meet irreducible. Okay. And just for later, I want to point out that this is a completely lattice theoretic term. I mean, so it corresponds to the meet irreducible elements of the lattice. So these are those elements in the lattice which are only covered by exactly one element. And this will become relevant in a slide soon. So this is the first theorem from this joint work that I mentioned. It should appear at some point. At some point. So the width of G for any finite group G is just the number of meet irreducible subgroups of G up to conjugacy. That's all I need. So this is really nice. We've managed to define this using intrinsic properties of the group based on types of subgroups. And you can actually write down the explicit basis. So you only have to consider transfers into G from the meet irreducible subgroups. So here, what I've drawn are just those, exactly those. So these are the meet irreducible subgroups, and I've drawn these arrows in. So this gives you an explicit basis. So in the first fun game, I mean, I've already shown you on one of the previous slides, number of meet irreducible subgroups of some groups, and I thought very naively, how hard could it be? Like, I take a family of finite groups G, and I just say, there's clearly this many things. Who knows how many maximal subgroups symmetric groups have? One. At least one. That is a correct answer to the problem. There is at least one maximal subgroup. If you've never thought about this, it might actually surprise you. We don't have a closed formula for the number of maximal subgroups of symmetric groups. There's asymptotic bounds, which I think were proved in the 80s and 90s, That's about the best we can do. The sequence isn't even monotonic. So the left-hand side column here, you'll see, for example, that S6 has 6 maximal subgroups up to conjugacy, and S7 only has 5. This feels very wrong in one's gut, but it is true. Again, if you're bored, why not write down all the subgroups of S7 and check? How hard could it be? But here on the right-hand side, I've listed the number of meet irreducible subgroups of Sn up to conjugacy. And you see that this is a very different sequence. This seems to actually be monotonic. I should say that thanks to the wondrous work of Dave Benson's coding, that I managed to get this past like number 7. I was using JAP, and I don't know if you know this, but JAP sucks sometimes. It really didn't want to do stuff with subgroups. Conjugacy was sending it into like some weird spin. Its data usage was strange. So Dave was like, I have magma, let's just use magma. So he wrote some magma code, which was far more efficient in these group operations we needed, and we managed to get the number sequence. So I don't know what this sequence is. These are kind of some numerical values we have. Ideally, I'd like to sit down and prove asymptotic bounds for these things, but we all know how easy the symmetric groups are when you really try and do stuff with them. So, cautionary tales, yes. So I already mentioned that you can work up to conjugacy a lot of the time. So this is the group sometimes called convenience 8. So it's it's 3 copies. C2 cross C2 cross C2, semi-directional C7. So these are Frobenius groups. This is a lossless group. So previous work says, actually, I can do transverse systems up to conjugacy, no problem. And I've already mentioned that from a lattice theoretic point of view, the meet irreducible subgroups correspond to those elements covered by exactly one element. So let's count. Well, this only has covered by one element, so 1, 2, 3, 4. So you say up to conjugacy, there's 4 meet irreducible subgroups. So the width of this group, the number of generators needed for the complete transfer system, is 4. This is wrong. Why? Well, it's because of this silly thing here. Really, I have like 8 copies of this down here, 8 copies of this here, and these, of course, 3 of these included each one of these. So you can't work up to conjugacy. You really have to do it in the subgroup lattice and then take conjugacy. You can't commute these 2 things. And I thought because it was like changing 2 things around, that was definitely a Jekyll and Hyde. But at this point in the talk, like I had this huge list of comics, and I was like, I'm running out of ways to like tenuously link this to slides. You have to take what you're given, right? So we've now looked at this, the width. So this was the number of minimal generators needed for the complete transfer system. I want to go back to this example that we saw of a CP squared Q, where although the complete transfer system needed 3 edges, there was a single thing at the end that needed 4. Like, what is that and why is that? So this is what we're going to define to be the complexity. So mathfrak C of G, the complexity, I look at all transfer systems and I look at the thing that has the biggest sized minimal basis. This is some measure of like how bad could it possibly be when you're computing these bases. Spoilers for the next slide. This actually gives us a non-trivial lower bound on the number of transfer systems. So the number of transfer systems is at least 2 to the complexity, which is going to lead to some disappointing news in a few slides when you see how the complexity grows, and then you're like, are we ever going to know the number for this? Probably not. So yeah, this is a non-trivial lower bound. So this is an interesting number, A, because it's going to give us a very strange invariant of the group G, and B, because it actually has something to say about transfer systems. So here are some numbers. You'll notice that we've kind of lost general formulas down here, and these have specific things. So again, for CP to the n, the complexity is n. That's not hard to see. We've seen already, or you've taken my word for it, that for CP squared Q, the complexity is 4. There was a transfer system that appeared in step 4. For the cube, so CPQR is 7. If I add another dimension for cube, I go to 16. For S4, it's 9. And for S5, it's 19. So immediately we see that this number is generally a lot larger than this width value was. And yeah, so into the maelstrom in that there seems to be no way to just say, here's a group G, give me an intrinsic property of G that tells me what this number is going to be. Like this seems really, really hard. I'd love to say it's the number of subgroups such that blah or something like this, but we've not been able to nail down anything concrete, which is alarming, but also fun at the same time. But I really hope that this is, I really strongly feel that this should be related to some intrinsic property of G. There's no way that this isn't intrinsic to G, right? It's something about linear independence in the subgroup lattice or something like this. And it's, yeah, I'm going to have to nail this down. So what I'm going to do for the rest of this talk is talk about an actual way that we know the complexity of groups of the form Cp to the nq and for square-free cyclic groups. So we can compute this without having computed all the transfer systems and saying, it stopped at step k, right? And this is good because then it can give us lower bounds in the number of transfer systems and some really crazy combinatorics. So I'm going to switch to some serious math now, talk about rainbows.
Yes.
So what's a rainbow? It's going to be a series of nested arcs. It's a finite series of nested arcs on the natural numbers. Here's a particularly nice rainbow. If it were to rain in Belfast like it normally does, you might have seen one of these today with the sun, but no chance of rain this week for some strange reason. So I really want a single series of nested arcs. I can't have two arcs which are disjoint. The whole thing has to be nested. So this is a rainbow. And I think at this point, I think it's Miguel who really pushed this idea back when we were first thinking about this of how these are actually relevant to what we want to do. So what I'm going to do, so I take the subgroup lattice of G, I take sub G. And I'm going to define a function that takes a subgroup H and sends it to the sum. So the size of H, I can write this prime decomposition as P1 to the N1, blah, blah, Pk to the Nk, and I just sum up the powers, these Ni's. You can do this, and I'm going to tell you why you should do this in a minute. I'm going to abuse notation. I mean, who doesn't? So P is also going to be a sense to intervals, right? So I can just apply it to the first and second element of an interval. It still gives me a perfect map to intervals of n. So this is a strange function. The word abelian appears in red here. I don't need abelian groups, but if I assume non-abelian, I have to write more things on the slide. Anyway, so S is going to be a set of non-identity elements of intervals, right? So I'm just picking a collection of norm maps, if this is how you want to think. And I'm going to apply this map P to it. I'm going to project it down to the size of the subgroups and sum up the coefficients. And I can ask, does this give me a series of nested arcs? Is this a rainbow? And this seems weird that everyone wants to do this, but it's weirdly efficient at solving these problems. Because what we can prove is if S is one of these partial rainbows, so its image under this P map is a rainbow, then it is a minimal generating set for some transfer system. So it's a great way to cook up minimal generating sets in general. Here's an example. This is CPQR, so this is a cube, drawn not as a cube. And what I'm doing, so I've laid it out in the way that the projection map, these all have exponent 1, right? So these will get sent to 1. These will have 1 and 1 to get sent to 2, help under sent to 3 and to get sent to 0. So I have these non-trivial edges here, and I project down. This edge now goes from 0 to 3, and all of these are the form from 1 to 2. So this does project down to a rainbow, and indeed, this is a minimal generating set for the transfer system that it generates. There's 7 edges here. Actually, this realizes the complexity of this group. Okay. So the neat idea. Look at pre-images of rainbows. I could do this. And weirdly enough, sometimes this actually gives you the number of the complexity. Specifically, it seems to be very efficient when I want to switch things like prime factors. So I think about the cube, I don't really care if I switch P and Q, right? It should be the same. These things should somehow be symmetric along these things. And what these rainbows do, they really build in this symmetry into the problem. Okay. So let's try this for Cp to the NQ. I'm going to cut into things almost like if I had a pit and a pendulum. It's getting tenuous, I know. And it turns out you have to consider two cases, n being even and n being odd, and the two behave separately. So hopefully I can describe what's going to happen here. So n is going to be even. So Cp and Q, n is even. So the subgroup lattice, I mean, I will draw this here in general. Right, my subgroup lattice is nothing more than this grid, right? So I have one dimension here, and here I have n, right? So the image of partial rainbows, so if I apply this map P and I push sub G down to the natural numbers via this method, here I have the subgroup Cp to the n cubed, n plus 1. Well, if n was even, this is going to be odd, right? So this is going to land at n plus 1, and n plus 1 is odd. And I'm saying here the pre-image of the rainbow with all intervals is maximal. This means nothing to no one, maybe aside from me. So let me see, let's show what I mean. So here's my example again of Cp squared cubed. And I'm going to project down, right? So I've applied this map P. This projects this to 0. These two groups have coefficient 1, they intersect 1, 2, and 3. So this is my projection map down. So now I'm saying I want this to be a rainbow on 0, 1, 2, 3. There's an obvious thing you should pick if you're going to do this, right? I just draw this. I mean, I don't have to miss anything out. I can draw all arcs, so I connect all up nicely. So this is what I mean by kind of the rainbow with all intervals. I just draw the maximally sized thing. Then I have to pull this back. So it's saying I should have a map between anything that gets mapped to 0 and anything that gets mapped to 3. This gives me the map from 1 to here. This is telling me that anything that lies in this row should map to anything it can that lies in this row. Here's what I made earlier. So you can do this, and we've already seen this shape before. This is exactly the 4 edges that generate this kind of odd one out transverse system. And indeed, this is the whole point, right? I'm trying to find the complexity, and we're saying this does the trick. And you can very quickly see, so this edge, so if I do this for general n, this long edge here only ever contributes one thing. It's the edge from the trivial subgroup to the whole group. That's length 1. This contributes 1 to S, my generating set. And then these other ones, these intermediate arcs, always contribute 3 edges. That's what they contribute. You sum all this up, and you get 3 to the k plus 1 if n is 2k. And I did assume that n is even. And then you have to do n is odd. And you might see what the issue with odd n is here. Here, it was very nice, right? I just picked the maximal thing. So if n is odd, so again, the subgroup lattice is the same. I map down to n plus 1. But what I need to, but now I map down to 0, 1, 2, 3, 4. I want to draw a single family of nested arcs on the numbers from 0 to 4. I have to miss something else. Someone has no friends. Also, this has no friends. So I have to pick which one to miss out. And you have to really sit there and think, well, if I miss out this one, what's the pre-image going to look like? If I miss out this one, what's the pre-image going to look like? So here, I've missed out the number 4. I said, he came at the end, he's late, he doesn't get to be in the group project. I pull this back and I get this. Okay, so this one again. It turns out, and I'm not going to go into the details of this one, but this is the best case scenario. I either miss out the first thing or the last thing, and this will always maximize the combinatorics of this problem. So again, we have these 3 edges on the intermediate arcs, but now this edge here, it contributes 2 things, as you can see here. So the total count is 3 to the k plus 2. Here's the theorem that we proved. So G is Cp to the n cubed for p and q distinct primes. then these maximal rainbows I've described do actually realize this complexity. This is the worst case scenario. And yeah, if n is even, it's 3k plus 1. If n is odd, it's 3k plus 2. The number sequence is non-multiples of 3. I mean, so these results come out of this MRC project, which is already mentioned a few times this week. And I went along to this MRC with my code. I had these numbers, and I was like, look, my code's probably wrong. It looks like it's non-multiples of 3. What a stupid number sequence, is clearly a mistake. But no, it's true. The code was correct, and you know, there's multiple ways of saying this. We did it via rainbows. Another way you can think about it is just like fitting things in, like this diagram I had for CP squared cube. You try and extend that, and you realize you can't extend it in kind of interesting ways. So yeah, you get non-multiples of 3. In particular, this is a linear sequence, doesn't grow very quickly. This is the last time we're going to see a nice sequence today. So you say, let's do it CP squared Q squared. Here is the maximal rainbow for this. Lovely, it's symmetrical. It has 6 edges. And you're like, let's just prove the theorem here as well. You can't, it's wrong. Here's a generating set with 7 elements. It's minimal, there's no redundancies here. This generates a transfer system, it's a minimal basis. So rainbows fail.
Yeah.
These things happen. However, there is a potential solution. So again, this is a great idea that Miguel came up with of double rainbows.
Yeah.
Yeah, double rainbows. How many of us are that old? I don't know. So this gadget here is a rainbow. This gadget here is a rainbow, and they're connected by these 2 edges. And if you do the combinatorics of this, you get some very promising results. It looks like this might actually work. But this method does break down as soon as you extend a dimension upwards. Okay. So let's talk about square-free cyclic groups. Cubes. Subglass is cube. We just did the same trick again. So I'm going to compute the maximal rainbows. I take the subgroup lattice, which is just 1 to the n, it's the n cube. I push down using this map P, this goes to the lattice n. And this is now just kind of very standard combinatorics. In my school, you can work out if I have an edge from I to j in here, and I pull it back, this is the number of combinations you get in your cube. This is just, you look at the combinatorics, you write it down. When n is odd, we get the same thing. We have this maximum arc thing. There's no choices to make. Everyone's happy. I was happy. But when n is even, there's something to check, right? I have to miss out one of these things. And again, I went to the MRC. I was like, here's the code. This is definitely correct. Like, how hard could it be to prove this? And wow. Wow. Yeah, so suppose n is even, I need to work out which node I to leave out. Like, how hard could that be? Like, it's combinatorics. It's like binomial coefficients. We can use binomial coefficients to log these things. It's a disaster. So we have to check this. So this is what you get if you leave out the start point. This is what you get if you leave out the midpoint, and you can probably convince yourself, sat in your seat now, that if it's going to be leaving out one of them, it's going to be the start point or the midpoint. And you have to prove this inequality. If anyone can prove this in less than the 10-page proof we have, please. So this is true. Comma. As soon as n is 8. Before n is 8, this isn't true. Something to do with growth of binomial coefficients. And the proof we have uses some crazy recurrence relations since we've got reordered numbers. It's not straightforward. We thought this should be super easy to prove. Like, we even asked on Stack Exchange, like, you know, I mean, there's people out there, you know, people who've done math Olympiads who just like eat this stuff for breakfast.
Yeah.
We posted it online, nothing. Like, that's when we knew that something was not good. So yeah, I want to point out all we've done here. So the difference between these two is you add 1 here and -1 here. So you're balancing out this +1 and -1. This is as soon as n is 8, this goes wrong. Here's the theorem. Yeah, so if you square free cyclic, okay, so this is like 99% theorem. There's still something that needs checking in the fact that the maximal rainbow is realized complexity, but it's true. So when n is odd, we get this nice binomial sum. When n is even, and at least 8, we get this. And when n is 2, 4, 6, we get this. And this was a situation I turned to the MRC again. My code had done the stuff for like 4 and 6. And I was like, it's probably this. And we were trying to prove it. And then we wrote some more code, and then things went south very quickly. And it's taken us a long time to actually prove this inequality. It took a lot of effort. So what does this number sequence look like? This grows massively. So this is not linear at all. It grows very quickly. And I mentioned earlier that this complexity number gives us a lower bound on the number of transfer systems. Yeah, so that's obviously shouldn't be p to the n, this should be p to 5. So we know how many transfer systems there are when n is 4. When n is 5, we can now confidently say that there's at least 10 to the 15 transfer systems for this. So any algorithm that finds these, we want to store them, right? You say, let's be really, really generous and say I can store the entire data of the transfer system as a single bit. Obviously not. So it stores a single bit. There's still about 10 petabytes of storage. This ain't happening. I mean, we're not getting this number. So the story ends for square free cyclic groups. I really think the way forward with computing the number of n-infinity operads or transfer systems for these square free cyclic groups is 100% to use this kind of stratification method. How many things are generated by k edges? Sum it up. I really feel like this is the way forward with this. Okay. So I'm going to finish a bit early, which I think is nice, given that we have back-to-back talks. People can take a breather. I just want to bring up 2 problems which I want to point out. So the future, we've had some answers, but there's still many questions and quite the odyssey ahead of us. I know. I showed my wife these slides and anyway. So we've looked at 2 families of groups. Another family of groups I could look at are the elementary P abelian groups, right? Super nice family of groups. And this is currently a conjecture. And you'll notice that this looks almost identical to the square free cyclic case. This is not a typo. They literally look almost the same. Difference is behavior change at n equals 6. And these aren't binomial coefficients anymore, they're Gaussian coefficients. So these are the Q analogs at binomial coefficients. This is really strange, right? Because these Gaussian coefficients are defined, so if I take the limit as p goes to 1, I get the binomial coefficients. In what sense are square free cyclic groups some limiting factor with elementary abelian p groups? I have no idea. So I think this is true. I'm pretty convinced this is fine. I can't prove this. I don't know if you ever tried to prove things about Q analogs or various combinatorics. These things are not easy. Our proof without the Q, like I said, is like 10, 50 pages. I don't know if it's probably gonna be much harder, right? When I do these Gaussian coefficients, but I would really like to think about this and see why the behavior seems so similar to the square free cyclic case. And this is the weird one. So we've already seen in CP squared Q, there was a single transfer system realizing the complexity, right? Out of the 68 transfer systems for CP squared Q, only one of them needed this basis size of 4. This happens quite often. It doesn't happen all the time. So for example, for, let's think, CP squared Q squared, there's definitely more than one that realizes the complexity. Right. This also happens, for example, for the cubes. So for these square free cyclic groups, as soon as whenever you're odd, there's a unique realizer. Whenever you're above 8, you have a unique realizer. It works for S5, but not S4. S4, there's 27 transfer systems that realize the complexity. For S5, we saw there's 850 million transfer systems. One of them needs 19 edges. 1 in 800 million. Why? This is some very strange property about subgroups of groups and intervals of subgroups in a way that I can't even begin to imagine. And, we've already had a comment earlier this week, I'm sure if you show us the right people, like, well, duh, it's obviously blah. But finding the right people to ask questions like that is difficult, right? And then the final slide, shameless plug, as one should have, again, talked. I mean, a lot of you have been working with this topic called combinatorics or infinity operads or transfer systems. Many of you might have heard about this story before this week and think, I could do some combinatorics in my spare time. So last week, I finally released my entire library of code for doing these things onto GitHub. On the archive last week, I posted a full documentation of how to use this. It is written in C++, but the code is done in such a way that even if you don't know how to use C++, you can still do this. So if you want to get involved, if you want to start plugging in groups and getting out numbers, and we've already seen again this week that this is kind of great work to do with people like undergrads. They appreciate what a group is, and it's a little bit of research that they might be able to get involved with, and I think we should definitely promote this. So that was in the hope of trying to get more people involved without this barrier of like, I don't know how to use C++, and there's only so many emails I can deal with about computer transfer systems. On that, thank you very much.
Yeah, it may have been a back to you that I've been like sort of serially harassing members of your group with questions like along these lines. But I'm curious if like the equicardinality of generating sets for a given transfer system is really fascinating to me. And I'm curious if you like put on like kind of combinatorial topology classes on this at all and studied minimal generating sets from like a simplicial complex point of view?
Nope. I've not thought about this. I mean, I think a lot of this is very early stages, right?
Yeah.
And I think there's a lot to be said here. I mean, the generating set seems to generally contain a lot of information about the group, especially the two extremes I've spoken about today. And, as always, everything in between should also be of equal value somehow.
So you gave a number of results on the width for the various groups.
Yeah.
All of which for cyclic groups would be consistent with the conjecture that the width of a cyclic group is the number of prime factors in the order.
Yeah.
With multiplicity. Is that true?
That should be right, because that's the number of meter address for subgroups.
I was gonna ask, can you share a little bit more about why, when you're working in the case where it's odd, that your rainbows are like, that the best rainbow isn't the one where you skip the middle? I don't know, this felt like the natural, like, best one, but then you mentioned that.
So the best case assumes your n equals 8 is to skip out the middle.
Say that again?
So as soon as your n equals 8 in even, yeah, I mean, skipping out the middle one is the correct thing to do.
Okay,
And that gives you like this, there's only one rainbow like that, so it's unique. And then
right,
just before then, I mean, it's weird that you skip out either the first or the last thing. And,
right,
we have a proof of this fact, but I don't think we have a comprehension of why this is true.
okay,
It's definitely related to growth of binomial coefficients. But like, we don't have anyone, well, I don't know anyone very well who like really understands the analysis of this sort of thing, or has thought about exponential growths of these sort of things or anything. I mean, you could probably prove this using asymptotics in a very neat way, but we have this kind of very almost brute force approach of just proving it's true.
yeah.
We came up with a bunch of invariants. Do you have a sense of what these things are invariant under?
In what sense?
I mean, certainly the isomorphism invariant.
Yeah,
So
so.
other kind of sameness relations of groups or which give you.
Yeah, so we've not really investigated this. So I mean, I think the width in the abelian case definitely is multiplicative. The complexity we've already seen is somehow not multiplicative, I don't think. But I haven't, for example, checked if I have a group extension, if you can bound the group extension by the pieces and things like this. I mean, like I said, it's very early days. But yeah, they're definitely, we've already seen that somehow these lattice constructions you might do just don't interact nicely with the transfer system. The hope is some of these invariants might.
Okay, one more quick.
Do we have any calculations on like how many disk-like or saturated transfer systems, can you adjust your code to?
Yeah, the code has literally everything you might ever want. So if it's been defined in the literature on transfer systems, I've written an algorithm for it.
Right.
So number of co-saturates, number of saturates, number of model structures, number of compatible pairs, number of things on the underlying lattice without conjugacy, number of transfer systems on the post set up to conjugacy, like everything is there.
Perfect.
Okay, thanks, Scott, again.